Thank you so much for the invitation, organizers. News is always something that is a first. So this is my first in-person conference since January 2020. So anyway, alert the press. Thank you for the invitation. I actually taught for the first time in over 2 years on Monday in person, and that was weird. It was weird. Anyway, because I had the teaching schedule, all this, and I had organized an INT meeting in January 2020, just prior to the world shutting down. Anyway, so wonderful to be in person, and sorry to be late in joining you all. I had other obligations, mostly teaching, so including this morning. So I got to hear a lot of Graciella's talk, and I'll be covering a little bit the same ground. I was thinking, how does my talk fit into a lot of the stuff that has been seen before on interdisciplinary developments in neutrino physics? A lot of this is about cross-section work that I've seen, a lot of nuclear particle neutrino physics. And this is going in another direction of interdisciplinary work, and we'll see how. So if you've seen a talk of mine recently, you've probably seen this, that neutrino mass generation is an original hidden sector theory. It doesn't get much credit for that, though. The simplest models of neutrino mass produce sterile neutrinos or introduce sterile neutrinos that generate small active neutrino mass scales from very massive sterile neutrinos, seesaw models. Andre de Gouveia and others have worked out just these simple insertions of phenomenological Majorana-Dirac mass terms as a way of introducing neutrino mass. They could be connected to some seesaw mechanism, of course. So you need at least two massive 100 GeV sterile neutrinos to produce the two known neutrino mass difference scales, the atmospheric and solar scales. And so I would argue it's the only hidden sector model with evidence for its existence from the lab. Third sterile neutrino has complete freedom. Let's say we want a third because there's 3 families, but maybe there's actually more. There's no reason that the number 3 is special. But anyway, if you have another neutrino, it could be mixed with the others, and if it's associated with the lightest neutrino, most with the lightest active neutrino, then it could have an arbitrarily small mixing angle, also unbounded from below, and that's important because for dark matter production, you want to have a small mixing angle. So now I just swapped out 2 words on the previous slide with 2 other words. And, you could be cool by using these words as opposed to sterile neutrinos. All your BSM friends would include you in their discussions. Model builders would love, they love dark fermions. But it's exactly the same thing, right? Sterile neutrinos are dark fermions. I was actually lecturing this morning to an advanced particle physics special topics course, and a student said, I won't reveal who she was, she said, what if dark matter is not cold dark matter, but something weird? And I said, well, you mean like sterile neutrinos? But it's not necessarily weird, right? It's something a little less harped or promoted within the particle physics community, but certainly not neglected, overly neglected. So anyway, a history of the dark matter production models out there. It started back in the early 1990s with Donaldson and Woodrow talking about oscillation productions in standard thermal histories. This is where the 130 MeV number comes from that paper, actually. The resonant sterile neutrinos were worked out by George Fuller and Zhengdong Shi in 1998-99. I was a young, foolish graduate student then, and I was talking to my advisor, George, and Zhengdong, and they said, it would be good to actually do a more accurate calculation than what we did, and that's what I did. And we looked at all the constraints on things and on this dark matter parameter space, and we saw that Xray astronomy was actually the best way to place constraints. And also the production is near the quark-hadron transition, so you actually have to handle the quark-hadron transition very carefully. And what differentiates this model from this model is the resonant production model requires a non-zero lepton number, and that's just a single new parameter. And that parameter connects the two models because as it goes to zero, it approaches this model. And we did the full momentum space integral differential calculation of the production. Since then, I used to say this title is production of oscillation-based production of sterile neutrinos. Since about the mid-aughts, I think I may be wrong, but I think Alex Kosenko started the business of decay production. I was going to look this up, but I didn't have time. But anyway, a lot of attention was scalar Higgs decay as a mechanism for producing things outside of the requirement of oscillations. Of course, oscillations still can and do happen, but they are not necessary to produce the dark matter in these cases. So since this is a conference and not a workshop, I won't show you the integral differential equations of the production, but just show you a plot that describes it. Here's the probability of an active neutrino staying an active neutrino as a function of distance or time. And it's very small in order to get production of order maybe 10 to the minus 11 in the mixing angle squared. And the interaction rate is extremely fast in the early universe between neutrino scatterings. So in fact, you actually get a suppression due to the quantum Zeno effect. And then once it gets long enough, and also the thermal mass allows for collisional production. The thermal mass allows this angle to get bigger as well, the matter-affected mixing angle. So here's just a list, and I'm sure it's incomplete, of non-oscillation production mechanisms. Again, I think Alex is first, but I might be wrong. Singlet Higgs decay, split seesaw mechanism for gut level production. Generic scalar decays were looked at, vector decays. A lot of these are post 2014 or 2014 and later after the 7 keV line was seen. Okay. So the one that I went up to UCLA, which is between here and Irvine where I'm at, to work with Alex back in 2019 is this miracle production mechanism. It's his original 2006 paper that was expanded on by Kalliope Petraki and Alex. And there you've got this decay into the steriles. And the coupling required to produce the KeV mass scale is about 10 to the minus 8 in this coupling scale. And if you just introduce the weak scale for this singlet, then the decay time in the early universe goes as this. And when you put it all together, you just get an omega 0.25 naturally, therefore the miracle. So that was an interesting point that he made. And this produces a very particular spectrum of the meaning momentum distribution spectrum of the sterile neutrinos. And that was worked out by Petraki and Kosenko. And we calculated the transfer functions, meaning their impact on structure formation today in this 2019 paper. Okay, so bringing up cosmological structure formation, what happens with it? Well, if you have warm things like sterile neutrinos producing the structure, it's going to have less structure. Now, this is an old result. I think this is from a BBC article where Carlos Frank's group at Durham was arguing that there should be maybe a warmness to the dark matter to get rid of the small scale structure and also reduce the density of the central core of galaxies. And although this is not as favored as a solution as it was, it's still of interest as to where or how warm the dark matter is. So here's a plot that I made as a very young postdoc in 2001 at Fermilab when I joined the Longitudinal Sky Survey. And this is the matter power spectrum. This is basically the correlation function of density in K space. And this is how it is affected by massive neutrinos. So you can tell right away how this is very sensitive to the presence of massive neutrinos. The other thing it measures is the clustering of matter at the smallest scales. And here we're getting to a K value of 1 and 10, where the Lyman alpha forest probes this region. And the question is, how warm is too warm? Is there evidence for a small scale cutoff, or is there lack of evidence for the small scale cutoff? And this was something 4 years later, I started looking at, 4 years after that last plot, that really tried to see where the limit is of warmness. Where does this cutoff exist? And the answer was the cutoff was somewhere between the two red lines, the limit on the cutoff. But we actually don't know it's up there. It could be way down here. Okay. Canonical cold dark matter has a cutoff at about 1 million in H inverse megaparsecs. And this was pointed out by Zeldriag and Lowe in 2006. So we really need to, the question is it here or is it here? Where in these 4 orders of magnitude or 5 orders of magnitude of space is the cutoff of structure in the universe? And what we're looking at here is Earth mass scales, and up here are dwarf galaxy scales. So in order to get this, you put this distribution of matter on in a computer. You give it a Zeldovich push, as it's called, and then you let gravity do its duty. Okay. I don't remember if this is animated or not. It's not. Don't worry about it. Everybody's seen these simulations. So, oh, there it is. So you see structure form, and you get substructure, and you count subhalos, and you just put them on a plot. The number of subhalos, and here a proxy for mass is velocity of the maximum velocity of the host, of the galaxy relative to the host. And CDM has a lot of substructure, and warm dark matter has very little substructure of small scale things. That's all we're saying here. Great, so that's what we expect. And in fact, you can place limits on warm dark matter simply by counting dwarf galaxies in our local group. And that has been done by Cylindrical Sky Survey and by the Dark Energy Survey. Okay, well, I'll just say a quick word. There was a lot of interest back in now 11 years ago, amazingly, in the possibility of warm dark matter solving what's called the too big to fail problem. And if you remember, this was a time of economic anguish, and certain financial institutions were deemed too big to fail. And same with the galaxies in CDM simulations had velocities that were very high as a function of radius. This is a proxy for mass. So they had a high density, and therefore they were too big to fail at forming stars. Therefore, too big to fail. And these kinds of halos or subhalos were called massive failures. Nobody wants to be a massive failure. Therefore, you want to introduce something that keeps that from happening. And 2 keV thermal warm dark matter particle masses succeed at not being a massive failure. And in fact, this is put pretty firmly by Anderhalden and Company, University of Zurich group, that a 2 keV thermal particle is able to match all of the observations, including their radial distribution, total satellite abundance, and their mass profile. However, this isn't the case anymore. You don't get the number right, and we'll talk about it more. So there was interest, and I would say that the interest has waned, largely because of in 11 years, the arising of hydrodynamic simulations that show that the star formation in supernova can blow out dark matter through its gravitational effects due to the large amount of star formation in the very center of galaxies. So what is the relationship between particle mass and warm dark matter effects? This is something that constantly I get, and that last plot betrayed a bias of astronomers that a 2 keV particle defines what we mean. And of course, that doesn't define anything. It just means a certain particle's mass. And what particle that is a spin 1/2 fermion that is thermalized in the early universe. So it's not even a gravitino because it's not spin 1/2. So really, it's actually more like a sterile neutrino. But anyway, what is this relationship? Really, what we want to know is the free streaming scale of this thing that has a velocity distribution. And it goes as this classical calculation of the free streaming scale that can be used for everything from hot dark matter to warm dark matter. And that's what places this scale into smaller scale cutoffs. So thermal warm dark matter has a thermal distribution. However, it's diluted by a factor of 100 or more by the fact that you can't have fully thermalized keV scale things, or you would violate the Kausig-McClelland bound. You would, let's say, overclose the universe, but you would just have too much density for it to be our universe. So gravitinos are a case of that. Sterile warm dark matter is thermal in that it is produced from the thermal neutrino distribution in the case of oscillation production without resonance. So it's just a suppressed thermal. And then you actually get quark hadron effects, which we included. And so it cools things because it's produced a bit above the quark hadron transition. So that's the Dodelson-Woodrow model. And this is the Shih-Fuller model where the resonance travels from low to high momenta and actually is colder than Dodelson-Woodrow. We like to call it cool dark matter. Didn't really catch on. Pretty cool though. It is cooler in that its mass, the mass for a given free streaming scale cutoff is less than the mass for Dodelson-Woodrow neutrino. So, and we'll see this in a chart in a bit. Here's an example. So thermal 2 keV, that canonical number that was there was excitement about 11 years ago, is consistent with an 11 keV Dodelson-Woodrow neutrino and a 7 keV Shih-Fuller neutrino, which is interesting because that's the mass scale you would want to solve that problem and produce a 3.5 keV X-ray photon. So this all was worked out originally by Coulombi, Dodelson-Woodrow back in 1995 and then follow-on work. J.J. Cherry, my academic sibling, and Shinsaki Horiuchi back in 2017 showed that the Shih-Fuller resonant production mechanism was on the ropes. And basically this up here is non-resonant production, meaning Dodelson-Woodrow. This is mixing angle versus mass. And over here you get a lepton number that's too large for BBN to allow. You mess up BBN. So you have to live in this colored space with the rainbow space. And this is the lepton number that you would need in this space to produce the right relic abundance. And this is the momentum over temperature, average momentum over temperature of these things. Note they're coldest right in the middle here. And I'll show you why in a bit. So if you just do the thing of counting galaxies, you place limits. And that counting galaxies limit at the time, 2017, was about here. But if you make corrections for the fact, this is from Sloan Doodle Sky Survey, if you make corrections for the fact that SDSS is incomplete, then the limit was between the blue and the red. So I think it was at the blue, and that if when it completes its own survey, it could be pushed to the red. So why is it more or less thermal here? So if you look at this point parameter space and run it through the code that Teja Vanumidov and Francis Jan Sarasin and I and Chris Harada wrote in 2015, you see that it's produced like the Shih-Fuller mechanism in that you produce mostly very cold things. The resonance passes through and the P over T is relatively cold in this spot. However, if you go down here where you need a large lepton number, the large lepton number drives the resonance all the way across the spectrum and you produce a hotter thing, even though you have a larger lepton number. So that's what's going on. So your limits are non-monotonic. They have this like Pac-Man shape that we saw earlier. So the other way that things get interesting with sterile neutrinos as dark matter is that they are not entirely stable if they mix with the actives. The tree level decay is into 3 neutrinos, which is maybe of interest, but extremely difficult to detect. The loop decay produces a photon and a neutrino, where the mostly sterile thing decays into the mostly active thing plus a photon. And this was actually first worked out by Robert Schrock, and I think independently by Paul Wolfenstein. And since you have a massive thing and one massless thing and one nearly massless thing, the photon has the energy scale of the neutrino, which is on the keV scale, which makes it an X-ray photon. The decay rate is extremely slow, orders of magnitude. Its lifetime is orders and orders of magnitude longer than the age of the universe, so it's a good dark matter candidate. However, this is still very large when you multiply it by the number of dark matter particles in a typical cluster of galaxies like Virgo. When you multiply these things together, you get something like 10 to the 48 dark matter decays per second for the 7 keV or 3.5 keV feature. 10 to the 48 particles decay per second in a cluster of galaxies. That's like Avogadro's number squared or something, right? Very large number. So you can actually detect the result of those decays with human-sized telescopes like XM Newton, Chandra, and their successors. So this is where things sit in terms of placing constraints, and the interdisciplinarity comes in here. We've got constraints from Xray and soft gamma ray, hard Xray here all across the parameter space and mixing angle versus mass. This is where the 7 keV, 3.5 keV signal was for a 7 keV particle. There's a lot of interest there and a lot of work there. Maybe it's like the 17 keV neutrino, but it's basically there. It still straddles some of the parameter space limits. And this is, I don't know why this is repeating. Oh, why this is repeating is that these limits of counting go up to 3 keV from SDSS to now, for thermal Warnock matter, to 6.5 keV when you include the DES galaxy counts plus lensing constraints from quad lenses that are seen by the Hubble Space Telescope. So the original work was when Shinsaku was at UCI as a postdoc in 2013. He worked with his postdoc in 2017. And then there was follow-on work by Nadler and company, UCLA, Carnegie, Toronto group. And so what does that mean? So I showed this. This is something that I've been wanting to write up since September. But when you become senior faculty, as I do, you get put on all these committees. So since September, I've been wanting to write this up. But here's the results, and hopefully written up by the summer at some point. Here are the X-ray constraints we saw earlier. This is the lepton number limit that you can't cross with a She-Fuller case. Otherwise, you mess up BBN. Here's the limits from Cylindrical Sky Survey. It's this C shape or whatever that is. And it starts really pushing on the signals, okay? However, the Dark Energy Survey, plus lensing, does this. It wipes out everything. So as a She-Fuller mechanism for the signals, or in fact, almost the entire parameter space is ruled out. The combination of X-ray plus structure formation constraints. Now, that's, I think, news, like a first kind of thing. And so, but you know, what about right here? Do the contours cross? I don't know. So there's two places where things are actually questionable that really have to be explored. This lepton number limit is actually not very accurate. You take the electron neutrino lepton number from BBN and you say that's the lepton number for everything. And that's not quite true. You can actually sequester some of the lepton number in the mu and tau, and then it gets transferred a bit into the electron neutrino. So there's about a factor of 2 uncertainty actually as to the level of this limit, 2 or 3. And then this contour has some unexplained features. I want to make sure that this is correct. So that needs to also be explored. So maybe there's a corner for She-Fuller, George. It's not all over yet. But you know, if people keep talking about your model, it's not a bad thing, right? All right, so what's going on now is in terms of getting the best possible constraints, and I get to present a paper that is submitted to PRL, but because it's led by astronomers, it's not on the archive, is strong lensing constraints on substructure. So this idea is you have a source, quasar or other galaxy, bright galaxy, usually quasar, goes around, goes through, its light goes through a lensing halo, and you get quad images of that quasar, and you can resolve them quite well with HST. And in fact, Anna Nierenberg at UC Merced led a proposal, which I was fortunate enough to just be the theorist on there, to get JWST cycle 1 time, and it was successful. So we will actually get a probe from JWST of stellar neutrinos and other kinds of warm dark matter. So the idea is that you would get less structure, of course, in the lensing halo, and you can model that, and it takes a bit of work because you have to marginalize over the inferred halo distribution and the substructure, but it's doable, and it's been done, and that's where the Nadler limits came from. And JWST will have unprecedented capabilities of mapping those lenses. Okay. So, thank you, PI and Ehrenberg. This is where they all actually are when you don't include the galaxy counts limits as well. So it's about 5.3 keV. It's hoping to push it above 10 keV thermal Warm dark matter particle mass. And so this paper that was just submitted last week was led by Ioana Zelko at UCLA, working with Tomaso Trejo, myself, Alex Kusenko, and several others. The thing is, you have thermal distributions, you get suppressed thermal distributions for Dodelson-Woodrow, and you get even colder things like the miracle model for decay production. And if you get a high scale gut scale production through decay, you cool down by another factor of 5 or so. So you actually get extremely cold sterile neutrinos in some models. So when you put this together, this is Ioana's paper. This is for the Kusenko 06 or Petrarca-Kusenko model. I sometimes call it the PK model. And remember in that first plot that I was showing of my work in 2005, the limits we were exploring were between 1 and 10 keV, 1 and 10 in K, H inverse megaparsecs. And now we're pushing really out there, out to very, very small scales with between thermal warm dark matter particle masses, and of like about a keV to about 20 keV. So, and the reason we show this plot is that not only that the thermal nature of the distribution or non-thermal nature of the distribution affects not only this momentum distribution, but it affects how the clustering behaves. So thermal warm dark matter particles have this dashed line. However, in this model of sterile neutrinos, it has a slightly shallower cutoff of small scale structure. This is the ratio of the two power spectra, CDM versus warm dark matter. Therefore, you don't see that K to the -3 behavior that's been scaled away. Okay, so this is the main results. This is a table in the paper looking at all of the different kinds of sterile neutrino and thermal neutrino models. This is the Petrarca-Kusenko model. This is KTY, the gut scale model. This is a Schief-Fuller new minimal standard model mechanism. This is Dodelson-Woodrow, and this is thermal warm dark matter. And so this paper actually places the strongest constraints on the nature of dark matter yet at 9.7 keV for thermal warm dark matter. And that translates to different numbers for the sterile neutrinos. So this is for strong lensing plus galaxy counts. This is just the strong lensing. And then this is in comparison with Lyman alpha bounds. And this case is when you make assumptions about the thermal history of the IGM, you get stronger constraints from the Lyman alpha. But this beats all of them. So a novel result. All right, so I think I have only a couple minutes left. Let me just talk about two other interdisciplinary things. We expect the Prism mission to launch in 2023. It will be able to have velocity spectroscopy capabilities at 4 eV level, so that if you have a dark matter line in a spectrum, you would actually resolve the velocity dispersion of the dark matter, which is amazing. There's also another thing being launched in China called the Enhanced Xray Timing Explorer. It's got this instrument on it called the Wide Field Monitor, and it's actually what I would design to be a sterile neutrino dark matter detector. If you look at it, it's basically zero optics. It's just detecting X-ray photons over a huge range of the sky. There's a lot of dark matter in the sky, so it actually could have very good sensitivity. And we pointed this out as a side project to a paper that we worked on for velocity information in the sky from high energy resolution spectroscopy, like from Prism, Athena, and Lynx. So this is where things stand. There's some forecasts for Prism that were published by Ando and company, as well as for eRosita, Athena, and EXTP. This is an arc curve, actually. There was another paper looking at EXTP, but they didn't look at WFM until we pointed it out. And WFM, if they can handle the systematics, has extremely good sensitivity. So This actually has to do with what we just heard about from Graciela. There's Tristan, Hunter, and Ptolemy out here will be able to probe these low reheating temperature universes, but I won't say much more about those because Graciela did. And it's of interest to keep in, to watch these. This is, if I were to say interdisciplinarity, this is the interdisciplinarity in one slide. We have constraints from galaxy counts here, from cold and warm dark matter, constraints from large scale structure and hot dark matter over here, constraints from X-ray astronomy here, constraints or signals in supernovae here, and laboratory experiments throughout, including beta decay and neutrino stellar beta decay. Oh, and don't forget the CMB. All right, so just in summary, stellar neutrinos' impact on cosmology and a candidate as dark matter has been investigated for about 30 years or more. Structure formation constraints are now at a really strong level, Zelko plus. We have it at about almost 10 keV level. When you add X-ray limits, it actually excludes all oscillation-based production mechanisms, or maybe nearly all excludes, as all of the dark matter. And look out for results from JWST related to sterile neutrinos. Mixed cold plus warm dark matter models. I took this out, but this is of interest. They would be, I went through it very quickly. They're relatively unconstrained. You could get a signal in the X-ray, let's say at 7 keV, but it would not affect structure formation significantly if it's only a small fraction of the dark matter. And that's what happens in lower heating temperature universes. Or could happen. Colder non-oscillation based production models have much more freedom, and then pure counts of future X-ray missions will do well. Rosita is flying. Prism should launch next year. EXTP in a few years. Athena and Lynx are 10 years or more away, but we'll be doing neutrino astronomy. Oh, and that's it. Thanks.
Time for questions and comments.
I have two, but so the first is so the amount. I guess that the size of the spectrum of the different structures, the amount, the number of the structures is what you are trying to see with the lensing, right? So the power spectrum essentially tells you how many of some size with respect to another, with respect where you can see a cutoff. Is that correct?
Yeah, the power spectrum is the linear information, the thing that's arising out of the early universe with no collapsing halos yet. It's the pure linear evolution, and then you put that into a computer, because there's no other way to do it.
And then you get this. Now, does it depend essentially where the maximum is in the spectrum? Or does it depend on some other features, tails or something else?
In this case, you mean
for the sterile neutrino initial spectrum, momentum spectrum?
It depends on every part of it because they're all clustering. They're all part of the dark matter. And
I see. So you have in every case you have to compute the particular spectrum.
Yeah. So
maybe different.
Right. In 2005, when I was one of the very few people looking at sterile neutrinos in structure formation, I had to modify CAM to do it. Now it's actually built in to a class, and at least a class, I'm not sure, it might be in CAM as well, to put in a table for the spectrum, and so you can put in an arbitrary spectrum. Note, if what you can play with it and you can break it, but what it is an integral differential equation. You have to do, it takes derivatives of the spectrum and
so it's much more right. So you have to compute the spectrum. That's very interesting. And my last question is the following: if it would be subdominant, as it is the case in most of the models that could be important for Hunter and so on, and Tristan and all this, subdominant. Do you have any constraint if it is not the dominant form of dark matter, coming from this type of structure?
Yeah, so that's an interesting question that has not been explored much. I know of really one paper that did it, and that was about 2010, and that's what produced the constraint in the low heating temperature universe model called CWDM. And they only explored like where the fraction was 20%, right? So, and also a certain mass scale, right? So there's 2 parameters at least to probe. And so this hasn't been done much, but I know that this is of interest and is being worked on.
So the statement would be still that if the sterile neutrinos account for less than 20% of the dark matter, there are no limits, essentially,
there are some limits because it can't be, say, 100 eV sterile neutrino in 20% of the matter. Then it's hot dark matter-ish, right? So there's this kind of overlap where it becomes hot and too much, and
I see. So there is an interplay between the mass, the spectrum actually, it's not the mass, the spectrum.
How there's the mass, the spectrum, and the fraction. So that's 3. Yeah, there's at least one paper that I know of, and that's cited in where that figure comes from. Yeah, I forget the authors.
So one thing I don't think you mentioned, Kev, is that the capability of Athena and Prism, for example, that's interesting is really high X-ray energy resolution, probably of order of a few electron volts.
Yeah,
4
I
or 5
mentioned
electron volts. And so, let's say that you train that Athena, which is more of a light bucket than Prism, on the Perseus cluster, and you look at the 3.55 keV line, and it turns out the width is very large, 36 electron volts, something like that. So then that stuff is collisionless, and it's at least some kind of component of dark matter. And then so where are we then? I mean, that probably won't happen, but I'm just saying it could, because that would eliminate the possibilities if that line width is large enough, it's the virial width, and it eliminates the possibility that it's some kind of atomic process involving potassium or argon or something like that.
Yeah.
And so, there are ways to make a relic density of 7.1 keV sterile neutrinos by slight dilation, for example, by invoking other particles at the chaotic equilibrium. So just wondering what you have to say about that.
Which part of that? Well, I mean, the velocity stuff is very exciting. I mean, we will know what's going on at 3.5 keV with Prism. We almost knew with Hitomi, right? It did an amazing job, even though it was up for a few days and still had one of the covers in place. But no, but not definitive. I didn't show the figure, but I can. Its limit and its sensitivity was so compromised by both the short length of time and the cover still being in place. But the spectroscopy was there. The 4 eV scale was there. They just didn't have the exposure. So yeah, it's going to be interesting when Prism flies successfully, hopefully.
Other questions? Can I ask one question, like very elementary question? The sterile neutrino that was studied is always assumed to be Majorana fermion. What could change if it is a Dirac fermion?
Not much. The decay rate is a factor of 2 different, and I think it's slower by a factor of 2 for the
mass itself would be the mass needed for the dark matter component wouldn't be shifted, or
I haven't thought about this for a while. It's a good question. My recollection when I did think about this, it was that the Dirac and Majorana nature did not affect the oscillation-based production.
okay.
George might know more, but I don't recall it being affected because it's just the mixing angle. It doesn't care about the mass generation mechanism. It's just the mixing angle. Yeah.
That's right. It does affect the potential. So there's a bit of a change in the potential. So you get a slightly different spectrum. I suspect that it's small.
Yeah. So it would be a change in the lepton number needed, maybe. Yeah.
Any more questions or comments? Well, if not, let's thank both speakers of this session.